Hello everyone, welcome to the latest lecture session. We've been discussing aspects relevant to calculating, not calculating if I may say so, maybe deriving the relevant variables. For example, we derived the concentration of the microbes X, let's say, the concentration of substrate or the food waste or waste in the relevant effluent, right? We calculated or we derived how to calculate the solid retention time and so on and so forth. So, let us try to bring this together and then look at designing a relevant what do we say activated sludge process, while also looking at the variables that we need to maintain, right. Let us get this started. So, typical aspects, right, quick recap: waste coming in at a flow rate of Q, this is the waste, and then we have the recycle flow coming in here. That is why here we have Q plus QR. Well, I should use X here instead of Xi, because whatever is in this tank, because we are assuming that the tank is a CSTR, right, is coming out here. And then we have the secondary clarifier or settling basin, wherein the flock forming microbes, they are going to obviously form flocks and then settle down. As they settle down, we will have clear water at the top, and that is going to be the effluent, let us say, right, and some of the sludge will have to be wasted. And we looked at different mass balances, as in we looked at the mass balance around the entire system. For calculating Q, recycle and such, we looked at the mass balance around this particular system, as in the clarifier, right. We are done with that. And then we looked at this particular what do we say schematic table, where we compared a fully mixed tank without recycle and fully mixed tank with recycle. So, major aspect is that typically I use theta. Sometimes people use retention time TR to represent hydraulic retention time, but I look at theta, let us say, right. V by Q same for both. Theta C for the case where there is no recycle is going to be the same as theta. The solids are going to spend the same time as the time spent by the water molecule. That is what this indicates, why there is no recycle. But with recycle, obviously we are increasing the theta C, meaning we are increasing the time that the microbes are present in your system, meaning the microbes now have more time to degrade the organics. Thus, the efficiency of the process is going to increase. Again, this is from the MIT open courseware. So, thus they would have used different or slightly different variables, but again we do not need to go into that in detail right now. We looked at this with respect to the variables that we use. For substrate, here with respect to the one without recycle, it is theta, right, but with the case of, or in the case of the one with recycle, we have theta C or the solid retention time, and obviously HRT a few hours typically, theta C a few days typically. So, obviously S is going to be much lesser for the case where we have fully mixed tank with recycle. S is the one, S in the effluent, let us see, right. And then U or substrate utilization rate, again that depends on mu, that is what we looked at, we are not going into that right now. X, one aspect is you can play around with the variables and get this equation. Again here we have theta, while here we have theta C, let us say, or theta C by theta is one variable here. And as you can see, the concentration of the microbes in the relevant plant will also be higher in the case where we have the recycle. And one other aspect we need to look at is, when we were looking at the case of the substrate or R waste in the treated wastewater, we saw that it is not dependent on S in, right, or it is not dependent on how much waste is coming into the system. Well, that seems a bit counterintuitive, isn't it? I mean, it is as if how much ever waste I put in with the relevant design and with the relevant theta C, it looks like my outlet or the concentration of the microbes, not microbes, pardon me, concentration of the waste or the BOD in the effluent is always going to be the same. How is that, right? It seems counterintuitive. Well, the trick here is in, I guess, understanding or looking at X, let us say, right, or X, this equation, let us say, right, as S in, right, the amount of waste coming into the wastewater treatment plant increases. What do you see? You see that X, which is the concentration of microbes, also increases, right. And if X increases, if you see it out here, if X increases, theta C will also increase, let us say. So, it is going to, or the system is going to self adjust, as in if the substrate, or there is more food for the microbes coming in, the concentration of the microbes will increase, right. So, in that effect, or in that scenario, you are going to have self adjustment of the system, and you are going to more or less end up with the same outlet concentration irrespective of the inlet concentration. So, that is something to keep in mind. And next aspect, as we discussed briefly, was oxygen transfer. Until now, we looked at what is the concentration of microbes that we need to maintain, how much time the microbes have to spend in the system, which is the solid retention time, right, and the design variable, which is the concentration of our waste or the food to the microbes or the substrate leaving the system, right. We looked at these aspects in different contexts. One other aspect obviously that is required from, what do we say, the engineer here, is the oxygen that needs to be supplied to the microbes. So, you need to be able to calculate the oxygen that needs to be given to the system. Well, one other reason why we need to be aware of this particular variable is that the major costs of operation of an activated sludge process or an aerobic process typically are due to the costs of pumping the oxygen in, right, or the air in. So, we obviously need to look at the amount of oxygen required. So, two approaches, we will look at the fundamental approach only, if I am not wrong today. The oxygen required, well, this is a particular way to look at it, but I will try to explain it in a better way. Oxygen required is equal to the oxygen required to fully oxidize the organic removed minus the oxygen equivalent of biomass solids. Again, this is the general version that people look at, but let us try to understand it in better terms. So, I need to provide oxygen and I need to know how much, right. So, where does it go? Some of it goes into, what do we say, degrading the substrate. So, I need to know the amount of substrate that is being what do we say, degraded in the system, right. And for that there will be a certain conversion factor, let us say, which I am representing by COS. But if you remember, in I think one of the sessions, probably a couple of sessions ago, we looked at the case where I think for a particular compound from the dairy waste, right, I think casein, if I am not wrong, we saw that not all the waste or not all the substrate goes into the final end products of carbon dioxide and such, right. Why is that? Because I think we looked at the vario or ratio being 5/8 and 3/8, I guess, and if I am not wrong, 5/8 of this particular casein went into what do we say, synthesis of new cells, right. So, here we are not really providing oxygen for the complete what do we say, oxidation of the organics, because some of the organics are being used by the microbes to form new cells, right. So, that aspect we have to remove, let us say, and that is what we have, let us say. So, we will have, we know the concentration of the microbes that are being produced, right, and we know that oxygen is not required for that particular reaction. So, we have the conversion factor for that. So, we have to remove it from this particular, what do we say, term or set of variables we have. This is the amount of oxygen we need to give if all the waste is to be oxidized, but we know that part of the waste will not be oxidized, it will go into cell synthesis, that is what we have. And if I need to look at nitrification, as in if I have ammonia NH4 plus or NH3, let us say, and I need to oxidize it, right. We looked at ammonia oxidizing bacteria, nitrite oxidizing bacteria in this context. Again, how do they oxidize? With the assistance of oxygen, obviously, right. So, you need the oxygen. So, whenever you have requirement of also removing nitrogen, so we have this particular term, right. So, that is what we have, that is a better way of understanding the relevant concept here. So, typical, what do we say, aspects or conversion factors, let us say, right. And with respect to nitrogen, you can see that it is 4.33 grams of oxygen is required per gram of NH4 expressed in terms of N units, let us say. Well, as you can see, a lot of oxygen is required. Again, you can look at the stoichiometry, you want to go from considerably reduced state to a considerably oxidized state. So, obviously, you need a lot of oxygen per each, what do we say, mole of nitrogen. Again, here the units are in mass, but again you can see that though, right. So, that is one aspect to understand. And with respect to ammonia requirements, let us say, we need to understand that in slightly greater detail. So, let us say I want to remove ammonia in this particular system and I need to know the oxygen requirement, fine. So, how do I understand the system? I know that it comes in the form of TKN, let us say organic ammonia and also free ammonia, if I may say so, right. and during degradation most of this organic ammonia will be converted to ammonia, let us say, right, NH4 plus, right, and then you are going to have oxidation, let us say. So, here I can assume that all the NH4 plus is being degraded. So, that is one way of calculating how much oxygen is required from the stoichiometry, let us say. When I say degraded, I am referring to oxidation of NH4 plus, that I can presume, right. But some of it will leave the system, yes. So, that is one aspect I need to look at, how much is leaving the system. And second aspect is that, again microbes are going to require some nitrogen for cell synthesis. So, some of the nitrogen will be taken up by the cells itself, and there is no oxygen demand due to this nitrogen content, let us say. So, these aspects we need to take care of. Let us look at what we have. So, Q into Tkn naught is the mass of nitrogen that is entering the plant, and for which we need to provide the oxygen, let us say. And some of the nitrogen will not be degraded, right, it will leave the plant. So, this we need to subtract, let us say. This is going to add, right, positive, and this is going to, okay, this we need to subtract. And as we mentioned, some of the nitrogen will be used for biomass, right, and is not going to be available for oxidation or nitrification. So, how much is it typically? It seems 12% of biomass, let us say, that is the N. So, 0.12 into Px, let us say, is the flow of nitrogen to biomass. Again, even this we have to deduct. So, now let us see what we have. So, here we have, earlier we had CO by S, I guess, CO by X are the conversion factors with respect to substrate, microbes and nitrogen. And then the mass of substrate, mass of microbes and mass of nitrogen, right. So, here what is PS? It is nothing but the amount of substrate that is being consumed for which we need to provide the oxygen. So, that is what we have here, Q into S naught minus S, initial concentration of the substrate minus final. So, that multiplied by Q will give me the mass of, what do we say, the substrate that is available for, or that has to be biodegraded, and 1.5 is the conversion factor. Similarly, negative here because some of the mass will go into cell synthesis, and this is the conversion factor. Px we already calculated it last session, and here we have the conversion factor for nitrogen, and Tkn naught is the one that is coming in initially, and this is the nitrogen that is leaving the plant or via the effluent, and this is the one that is being, what do we say, used for cell synthesis, let us say. So, that is what we have. This is the mass of oxygen that is going to be required to be supplied, let us say, right. So, that is something to keep in mind. So, different types of diffusers are available. So, diffused, so you want to create these kinds of fine bubbles or sometimes coarse bubbles, which I am not going into detail right now, let us say, right. So, again with respect to the kind of bubbles and such, obviously the smaller the bubble size, the greater the surface area, the greater the oxygen transfer efficiency, let us say, right, if I may use that term, yes. But again the issues are that you will have clogging of your relevant diffusers that lead to fine bubbles and such. So, that is trade off between maintenance and energy and oxygen transfer efficiency, let us say. So, what is the mass of oxygen? How can I calculate that? I know the airflow that is required, let us say. This I calculated from my fundamental approach, right, or I can calculate now. And this is, okay, one aspect I need to mention is that earlier we looked at the fundamental approach. This is based on the oxygen transfer efficiency approach, let us say. This is the flow rate of air, as in volume of air by time or with respect to time. Density of air, as in mass of air per volume of air, let us say, and the fraction of oxygen in air, let us say, right. So, the fraction of oxygen in air, right, or gram, okay, mass of oxygen per mass of air, right, into the efficiency, actual oxygen transfer efficiency. How efficient is it being transferred? So, what do we get? So, volume of air, let me use a different colored pen. So, volume of air cancel out, mass of air cancel out. So, the units that I end up with are mass of oxygen required per time, right? And depending on the oxygen transfer efficiency, we have to supply more. So, that is what we have, let us say, right. So, that is the mass of air that is required, let us say. So, this is the actual oxygen transfer efficiency which you need to calculate based on the relevant variables. Let us look at how we will do that. So, first we have to understand that there is a standard oxygen transfer efficiency and what are these standard conditions. These conditions are at 20 degrees centigrade for water that has dissolved oxygen of 0 milligram per liter calculated for tap water, and we are assuming a 4.5 meter submergence or depth. Okay. So, for these conditions the standard oxygen transfer efficiency is calculated, right. And how is it that oxygen goes from or is supposed to move from the gaseous phase into the aqueous phase, right? How does that occur? It is typically based on the two-film theory. Let us say if this is the bulk liquid, and here is the bulk air, if I may say so. Okay. So, it says that this is an air film or film of air, let us say, and this is a liquid film. So, depending on the concentration in the liquid, I am talking about oxygen, concentration of oxygen in the liquid and concentration that is going to be present in the liquid at what do we say equilibrium conditions, air in this particular or oxygen in the air will have to go through the film, the liquid film, and then into the bulk liquid, let us say. And what is the driving force? It's the driving force is the concentration gradient, and this is the relevant what do we say constant that will look at the surface area and the relevant aspects out there. And how is it, or in which cases obviously will you have greater transfer? So, think of this, if my water has no oxygen and there is a oxygen in the air that is in contact with this water, obviously the greater the difference between the concentration in the water and the concentration that can be in the water at equilibrium, right. So, then the driving force is greater, yes. So, the lesser the difference, the lesser the driving force. So, that is where this comes from, and KLA obviously will depend upon temperature. We have to correct it with for wastewater and for DO saturation also, but we will look at that, right. So, that is something to keep in mind. As you can see, this is C star is the one at equilibrium, and C is the concentration in the solution, current concentration, current oxygen, dissolved oxygen in water, let us see, right. So, that is how you can understand it. And how do I calculate AOT in terms of SOT? So, here we have different correction factors. One is alpha, because typically here is alpha. The mass transfer coefficients are calculated for clean water. So, because I want to calculate it for wastewater, I am going to have a correction factor. And beta is the saturation concentration in wastewater by saturation concentration in clean water. Why is there also a difference here? Because here you are going to have ions and other what do we say compounds or impurities that can affect the maximum concentration of the oxygen in your water. So, that is why you will have another correction factor for it, right. And this is the correction factor for the temperature, let us see, right. And CS is the saturation concentration of dissolved oxygen in clean water, and CL is the concentration of DO in wastewater, which is the actual concentration in your wastewater. From that you can calculate your actual oxygen transfer efficiency. And how do I, or is this always constant, or what does it depend upon? Again, PV equal to nRT and such. So, it depends upon the pressure again depends upon the elevation, let us say, right. So, okay, looks like I have to discuss another aspect here too. So, for diffused aeration system, what do we have? Average saturation concentration from average conditions at surface and full depth must be calculated, okay. So, as we were on the right track, so this will vary, let us say. So, that has to be calculated, and what do we need to look at? We need to look at the full depth, let us say, and saturation concentration at depth proportional to the depth, okay, and at the surface, let us say, right. So, these are aspects we have to look at, and it is proportional to the concentration of oxygen in air leaving the water. Again, all these formulas will be given, so you do not need to worry about it. So, how will I calculate the CS average? Right, it's we have the saturation concentration at the wastewater temperature and elevation H, elevation of that particular location, let's say, and pressure at full depth, right. For example, if the elevation is, let us say, 10 and the depth of water is 5, so PD will be 10 plus 5, let us say, right, and pressure at water surface, and that is what we already have out here. And here, what is this? Oxygen in air leaving the water. Typical, this is 21%, oxygen 21% in the relevant air, and this is the oxygen in air leaving the water, right. Typically 19%, 18%, it is going to be less than 21%, obviously. Again, one aspect, gentlemen, so what are we doing here? We know that there is a standard oxygen transfer efficiency. How efficiently will the oxygen be transferred from the gaseous phase into the aqueous phase or the water? So, to look at that actual oxygen transfer efficiency, we need to look at some correction factors with respect to, what is it now, wastewater, with respect to the maximum saturation, and with respect to what else, temperature, I guess, right. And also with respect to the saturation concentration, we know that it depends upon the elevation or the height at which the plant is located, and also the aspects related to the pressure or the submergence, let's say. So, these aspects we take into account, and all these, what is it, equations will be given in the exam, you do not need to worry about that. And equally importantly, you need to understand how the, or what are the variables at play here. That is one aspect, obviously, that you need to look at, okay. So, let us move on. Mechanical aeration, so as I mentioned, the rate of transfer depends upon the coefficient and the difference between the one at equilibrium, this is typically the constant, and the one in the concentration in the liquid, let us say. So, mass flow, right, I will have to multiply that by volume, let us say. And here we have other terms, aeration efficiency, mass flow of oxygen transferred per unit power consumed. So, this obviously takes into account the local conditions, let us say, with respect to the pumps and such, right. Standard aeration efficiency, standard aeration at, efficiency at standard conditions, let us say. This takes into account your pumps and energy, what do we say, efficiency too. So, that is what you have, again similar profile. So, we will not go into that in detail here. Again, all these are simple formulas, and once we give the relevant values, you just need to plug them in while keeping in mind how the units play a role, right. And obviously, people would always prefer that I solve homework questions or sample questions, but if I keep solving a lot of questions, right, or sample problems or numericals, we will not be able to cover the relevant aspects or the principles in detail. So, at least in this course, we are going to talk about the principles more and maybe less examples, but the TAs should be able to provide you the relevant assistance when required, or they can provide you the relevant solved example if you want to, right. So, that is something that you need to keep in mind. So, mechanical aeration, as I mentioned, fine bubble diffusers are more energy efficient, typically greater, what is it, oxygen transfer efficiency, but maintenance is an issue due to clogging, let us see. Power for mixing, typical power, you can understand the relevant energy requirements, let us see. So, now we will come across a term, I think I might have used that earlier, mixed liquor suspended solids, right, mixed liquor suspended solids. So, what is this about? So, you know that waste is coming in, and here we have our aeration tank and then our secondary clarifier, and considerable, what do we say, fraction of these the sludge is going to be returned, and some of it is wasted, and then we have the treated effluent water, let us say, right. And what do we have here? We know now that the concentration of microbes here is going to be pretty high. So, the contents of this aeration tank are called mixed liquor suspended solids, the contents. So, what does that contain? Obviously, it will contain bacteria, a lot of it, depending on how you are maintaining it. What else will it contain? It will obviously, or the MLSS will also include some inert solids or fixed solids, okay, inert solids. So, how do you distinguish between them? Again, these we call or try to measure anyway by MLSS, mixed liquor volatile suspended solids. So, you have a relevant furnace, and then increase the temperature, and then look at what is remaining, and that you say is fixed, and what I guess is not remaining, we call that as volatile, let us say, right. So, that is one aspect to keep in mind. And in this MLSS or such, what else? Is it only bacteria? No, you will have, looks like you will have some protozoa, 5%, and they also feed on the bacteria. So that's why you have the decay coefficient Kd, right? So that's one aspect, and protozoa seem to be playing a important role in leading to good sludge that can settle. So that's one aspect. And you will have dead cells, free swimming cells, or the motile cells, I guess, if I can call them. So you'll have different such what do we say, or you'll have a complex ecosystem in this MLSS. So what happens to the waste that coming in? The waste that is coming in will be immediately absorbed, let's say, or adsorbed by this MLSS. After that, the bacteria will oxidize or solubilize and then oxidize the organic matter, right? So that's how it's going to work. So we are going to call the contents of this tank MLSS, right? So let's move on. So solid retention time, some aspects that we need to be aware of. First, this is not HRT. This is about hydraulic or water. This is about solids, which when we say solids, we are referring to the microbes. So if SRT affects the properties of MLSS, obviously, why is that? I have this tank and this is the recycle, let's see, right? So recycle and the concentration, that will affect the time that my microbes are spending in my system, let's say. What happens if my residence time of the solids or the microbes is too less? So that can lead to sludge bulking. So here you want the sludge to settle down. But if the cell residence time is too less, it can lead to sludge bulking. We will look at that later, and it won't settle, let's say. Okay, obviously I have that out here, poor settling. And if settling is poor, then what happens? You know, XE, the concentration of microbes that are leaving the system are going to be high. Typically, you want that to be almost zero or negligible. But obviously, if they do not settle well enough, as in the sludge does not settle well enough, what are you going to experience? Obviously, you are going to see to it that some of it will settle down, it as in the microbes, and some will leave the system, let's say. And what happens if the theta is too high or too long, let's say? You can have dispersed sludge, and again small sludge particles that will lead to poor settling, let's say. Again, we will look at what this is or such, because not what, why. Typically, it's because of the kind of microbes, motile cells or such, you know, which have a lot of time, let's say, to be able to find their relevant food and such. Again, so the balance has to be between keeping theta c too short and too long, let's say, right? So that's one aspect. Typical SRTs, right? As I mentioned, soil retention time will be pretty high. As you can see, it's in days. In warmer climates, because obviously the temperature is higher, the kinetics or the rate of degradation will be higher. Thus, we can make do with lesser SRT. So that is why in India, even though the performance or the maintenance of the plants is poor, because of the warmer climates, looks like we are able to get it done. That's because the kinetics are pretty fast in general, let's say. Okay, let's move on. And one aspect, as we see, for a particular range, this is not for the entire range, effect of soil residential time or retention time on the settling properties of activated sludge, right? So typical range, yes, zone settling velocity, you want it to be pretty good, right? And I guess you see that with increasing SRT, you see what is it now? Better settling characteristics. But again, there is going to be an upper limit. This is the case for a 2000 milligram per liter of MLSS or mixed liquor suspended solids, right? Let's move on. So F by M ratio, right? So this is one other critical aspect. So food by microorganism ratio. So when we say food, it's our waste that we are talking about, obviously microorganisms. So we need to look at this ratio because we need to understand obviously the optimum conditions that will lead to optimal settling of the sludge and also optimal, what do we say, removal of the waste from the relevant or optimal removal of our food or pardon me, our waste from the relevant wastewater, let's say, right? So how to achieve that? There is a particular analysis. Obviously, we looked at the relevant aspects and derived the relevant variables. But let's look at the extreme scenarios. What happens when the F by M is too large, F by M is too low? But looks like I'm out of time for this session. So I'll end the session for now and continue this in the next session. Thank you.